Hi all, welcome to online spoken faculty development program and advanced communication laboratory. So this is session 2, experiment number 4, study of fiber optic digital link, and myself J. Kumarnath, assistant professor from the Department of ACE, PSNA College of Engineering and Technology. Yes, the core aim of doing this experiment is to study the fiber optic digital link, which means we are going to study the input as well as output characteristics of digital optic transmission through optical fiber. So before we just move into the topic, we should know why we are moving for this fiber optic digital communications. So there are many reasons for which we are preferably using this digital communications. Let me consolidate some few things, right? So the first important reason is it is error free, which means we can able to transmit the signal without error. So since the data is going to be transmitted without error, we can able to attain a maximum transmission rate. Since it is error free, maximum transmission rate can be attained, so we can use this digital link for very long distance, preferably for high bandwidth applications, right? And moreover, the data what we are going to transmit will be secure, and it is easy to integrate the voice, video as well as data. So these are all some of the few reasons why we are just moving for this fiber optic digital communications. So the basic apparatus which is required for doing this experiment will be simply a fiber optic digital transmission model, obviously, and fiber optic digital receiver model, an optical fiber, and an input signal from the 1 megahertz function generator, and at the receiver. So to obtain and to see the signal, we are going to use an 30 megahertz dual channel oscilloscopes. So these are all the basics apparatus which is required for conducting this particular experiment. So let me show you a simple fiber optic communication link. Normally for transmitting the signal over the fiber, there will be a need of a signal, there will be a need of a signal, and there will be a need of some transmitter. So listen carefully. So the signal what we are going to transmitted will be a light signal, hence there will be a need of some light source. It may be either LED or it may be a laser. For long distance we will preferably go for lasers, whereas for short distance and that too for experimental setup we can use LED. It's more than sufficient, right? So the signal is going to be transmitted over a fiber, hence there will be need of an optical fiber cable. At the receiver, the signal will be received in the form of light, so there is a needed medium to convert the signal from light into electrical. So there will be need of some light detector, preferably it will be a photo detector. So that is of receiver sections. At last we are going to retrieve the data out. So this is a simple diagram of fiber optic communication link. Let us see some of the few factors which influence the transmission of optical signal over the digital link. So it is important that the signal should be transmitted with proper acceptance angle and proper critical angle. So the acceptance angle is an maximum angle which is allowed by the optical fiber, so that the signal will be transmitted over the core of the fiber, whereas critical angle is an angle beyond which the signal will be transmitted with total internal reflections. So these two important criteria should be satisfied. So next important thing is the numerical aperture. So that is the maximum light gathering ability of the fiber, or the light collecting ability of the fiber. So this factors will depends on the refractive index of the fiber, which means we should maintain a proper refractive index. So refractive index of the medium is equal to refractive index of the vacuum to the refractive index of the medium, right? So the third important factor is the mode characteristics of the fiber. So this mode is nothing but the light ray which is going to be transmitted over the fiber. The last one is the signal should be transmitted without any attenuations or dispersion. So it has to be finely tuned so that the signal will be transmitted properly to the receiver. So let me show you a digital optic fiber link. As I just told you, there will be a need of an transmitter. The transmitter will be in the form of a light source. The transmitter will be in the form of light source. There will be a need of an optical fiber. There will be a need of an receiver. So these are all the three important component. If it is going to be a digital signal, then there is a need of an encoder at the transmitted sections. That is, the data has to be converted to encoded form so that it has to be transmitted over a very long distance, and at the receiver there is a need of decoder to convert the signal to its original form. So for digital optic fiber communication link, there will be a need of an encoder and decoder along with the analog setup. So this is a simple digital optic fiber link. So we can move to the theory part. As I just told you, so there is a need of a transmitter in the form of LED or laser. There will be a fiber to transmit the signal, and there is a need of a digital detector or a detector in the receiver part. So the signal which is to be transmitted will be in the form of binary, that is ones and zeros, and it is going to be transmitted over an fiber. In the transmitted part, there is a need of an TTL gate, that is an serial protocol to convert the signal or to drive the signal to the LED. So the LED in turn will provide an output signal in the form of light with respect to electrical signal. At the receiver, the signal will be received and it will be transmitted or it will be converted into an electrical signal with the help of an photo detector, and as usual there will be need of TTL converter at the receiver end. So this will be the theory behind the transmission of signal. Let us see the block diagram of our experimental setup. So there will be need of an TTL input to drive the LED. So the LED in turn will generate a light signal with respect to an electrical signal. So the signal will be transmitted over an optical fiber link and it will be received over an optical receiver. So the optical receiver will convert the optical signal to electrical signal and it will be given to the TTL converter, and the data will be retrieved out at the output end. So now just move into the transmission part. Important criteria. One is there will be an inbuilt function generator to generate an square waveform. Since it is a digital signal transmission, so we have to generate an square wave. So it will be given to the TTL converter so that the signal will be taken out. Other one will be an external digital input, so we can use an function generator and we can able to give the connection over this end. So the next part will be the LED driver. With respect to the signal from the function generator, the LED will generate a light signal and it is given to the optical connector. The connection setup is shown in the image, you can able to see. So we have to give the input over P3, that is an external or internal function generator. So the connection from the TTL has to be given to the LED driver to drive the LED signal. The signal has to be given to the optical connector, and from the optical connector the optical fiber has to be inserted. So this one will be the receiver module. The photo detector or photodiode to convert the light signal into electrical signal, and there is a need of a TTL converter at the output end to restore the original signal. So the connections of this receiver will be very simple. So the output from the fiber, that is other end of the fiber, has to be connected at the receiver optical connector. So the photo detector driver output has to be given as an input to the TTL driver, and by means of probe arrangement the signal has to be taken out and it has to be given to the CRO or DSO, that is a digital storage oscilloscopes. So this one will be a complete fiber optic digital link setup. Signal has to be fed from the transmission module, generate and light signal. So it has to be taken out by means of an optical fiber and it has to be given as an input to the receiver module. At the receiver module, so the signal has to be taken out through the probe arrangement. Here I have taken or given the input to the cathode ray oscilloscope. This one will be an advanced optical fiber trainer kit. So the important thing with respect to this particular kit is there will be an inbuilt transmission module, receiver module, as well as there is an option for optical fiber connections. Let me show you a simple connection procedure. So the signal from the function generator has to be given to the emitter circuit to emit an optical signal. So the output from the emitter has to be taken over by means of an optical fiber and it has to be given to the detector, that is optical or photo detector. So signal from this photo detector has to be given as an input to the comparator so as to produce an comparative output. So the signal from this comparator has to be fed to the amplifier to amplify the signal. So this one will be a complete connection layout. So you can able to see a complete output setup. So by means of this function generator we have to give an input signal to this particular advanced kit module. So this advanced kit module will generate an signal which has to be taken to the DSO, that is digital storage oscilloscope, so that we can able to see an output generated signal. The procedure will be very simple as I just told you. Before we are going to on the kit, it is important that we have to give a proper connection setup. So we have to provide a proper polarity, that is the power signal polarity. So we have to give an 1 kilohertz signal, that too in the form of an square wave. So once it has to be done, everything, once a connection has to be done, so we can on and you can able to see an output. At the receiver what we are going to do is we are going to take an we are going to note down the time period, that is T on and T off. From the value of T on and T off, that is from the time period, we are going to determine the value of duty cycle. So this is what we are going to do with this experiment. So this one will be the tabulation part with respect to our experiment. As I just told you, we are going to connect an function generator to the kit, right? So by means of function generator we are going to vary the frequency of the signal. So at the CRO or DSO we are going to find out the time period, so the two T on and T off. So the T on and T off has to be noted. From the T on and T off value we can able to find out the value of total time period of the signal. From the total time period it is very simple to calculate the value of bit rate. So the bit rate will be inversely proportional to T, that is it is equal to 1 by the time period, total time period. So we are going to calculate the bit rate. Then from the value of this T on and the bit rate we can able to calculate the value of duty cycle. So what we are going to infer from this experiment is, when the frequency is going to increase, the T on and T off will be decrease. If the value of T on and T off is going to be decrease, then the bit rate is going to be increase. So this is what we are going to infer from this experiment. So duty cycle is the total time period for which the signal will be active. We can able to measure the value by means of this T on and T off value. So you will get the signal like this. We have to measure this T on and T off. So from this value we can able to understand the characteristics of digital link. So next sessions, let me take you to the real-time environment of digital optic fiber transmissions, and it will be very interesting. So we can see in the next video. Thank you.